going to give you an overview of Chapter 3, which is different types of rules you can use to find derivatives. Just a review of Chapter 2, you have the power rule, and hopefully it looked like everybody did pretty well on that on the test, f of x. So if you have some type of polynomial, x cubed plus 2x, and I want to find the derivative, I just bring down the power and subtract 1. So that's 3x squared plus 2. So hopefully everybody was good with those. We had some special, I think we did the special cases, the derivative, which we're going to learn more special cases in this chapter. And that's where we start off right at the beginning. Right at the beginning, you're just doing what are called exponential growth problems, which uses this formula, a equals p e to the rt. So it's just straight using calculator work and knowing if I want to solve an equation. Let's say they want me to know the rate or they want to know the time. Since it's an exponential equation, I have to use the natural log function. So let me give you an example. Let's say that we deposited $30,000. We want to know how much is in the bank let's see that it pays 3%, and it has, if they'll tell you it's compounded continuously, which means that's the E function, compounded 3% for 5 years. So what I'm going to do is take the amount equals, P represents principal, so that's your investment. So I'm investing 30,000. E to the power of 0.03, the rate times the time, 5. And that's how it entered on the calculator. 3,000, you have an E to the X button on your calculator. And if they gave you what would be the rate if after 5 years, so they might ask it, how much time would I need for 30,000 to grow to 50,000? So then I would go 50,000 equals 30,000 e to the r, and then I don't know the time. So this is, I'm going to have to rearrange and use algebra, so I've got to divide by 30,000 first. So I divide those, get that answer. Then we always deal with opposite operation. The opposite operation, or the inverse operation of E, is the natural log. So I would take the natural log of this value, and then natural log of E, that cancels to 1, bringing down this power to 0.03t. That's just using the laws of logarithms, which means the exponent comes down in front, and then to solve for t, I simply divide by 0.03. So on my calculator, I just do natural log of this divided by 0.03, and that will be the time it will take for 30,000 to go to 50,000 at that percentage rate. All right, so that's first section, not really calculus, but just getting you used to solving finance questions, really, because this is a business calculus class. So then we go back to integrals, which remember is the rate of change. It's the slope of the tangent line. It's all of those things. So we have some special cases here. If I want to find if my function is some type of a natural log function, the derivative is a special case, y prime. It's simply whatever this function is, it's 1 over x. It's 1 over that function. And then you'd have to multiply by, we'll talk about a chain rule later, but for right now, it's the natural log of x. So if my function happened to be 4 natural log of x, it's just 4 times 1 over x, which ends up being 4 over x. So that's what we're going to work there. The other function is a very interesting function in calculus, which is really why it was created. The e function, it's the easiest derivative you will ever do because you don't do anything. The derivative of the exponential is the exponential. So in other words, the slope of the tangent line is itself. So at x equals 1, the slope is e. At x equals 2, the slope is e squared. So know those special cases. If they show up, you're going to use all your power rules, and then, I don't know, they might give you, let's just do a function. Let's say we have 4x cubed plus 2e to the x plus 3 natural log of x, and they want the derivative. So I'm just going to go piece by piece. This is a power rule, 12x squared. That's an exponential, so it just stays exactly the same. And natural log is 1 over x, so I just put it over x. So there you go. That is the first 2 or 3 sections there that you're dealing with special cases. Then we start different rules. The first rule we talk about is what's called the product rule. You have 2 functions, f times g, and I want to find the derivative of a product. So your function might look like, let's just take natural log since we just looked at it, natural log times the function x squared plus 3x. First thing that everybody wants to do is just to take the derivative of that one multiplied by the derivative of that one. That does not work. It's not the derivative. It is a product rule where we call the first function f and this function g. Your product rule to find the derivative is f prime, so the derivative of the f function multiplied by the regular g plus f times the derivative of the second function. So in this case, my function f, so f prime is 1 over x, we just learned that, times g, so 1 over x times x squared plus 3x, plus f, which is the natural log of x, times g prime, which is a power rule, 2x plus 3. It's not a pretty derivative, but that is y prime using the product rule. So that's just an overview of product rule, and your functions could be any types of functions there. It's just f prime g plus f g prime. The quotient rule is like it, or similar to it. So that means a quotient rule is I have a function divided by 2 different functions of x, and I want to find the derivative of that. So we've got the quotient rule, which says, so now I might have a function that's, I'll just put them, I'll just use the same functions really, natural log of x over x cubed plus 2x. So this is f and this is g. So the quotient rule is similar, except for it uses minus, so it's f prime g minus f g prime. And then you have to divide it all by g squared. So f prime is 1 over x times g, x squared, or x cubed plus 2x, minus f, I'm running out of room, g prime, 3x squared plus 2. So I'd leave all of that in the numerator divided by g squared, so x cubed plus 2x quantity squared. And that's your quotient rule. The next rule is called the chain rule. And it's not necessarily a product, it's when you have a function inside of another function. So it's going to look like, I've been using natural log, so I'm going to keep natural log. So instead of natural log of x, you have another function of x. inside of it, x cubed plus 2x, which natural log has a derivative, natural log of if this were x, and then this has a derivative. So this is what we call a chain rule. It's when you have a function f of another function inside. So f of g of u. So the idea is we're going to introduce a new variable called u. And I'm going to, u is just the most complicated part of your function. It's the what we call the baby function, the one that's on the inside. And my mother function, in this case, my mama function, is the natural log of this little baby function, because baby function is on the inside. So that's x cubed plus 2x. And so now I can rewrite y as the natural log of u, because this is u. So then I find dy, and that's dy with respect to u, because that's my variable. So now it's just the normal natural log, which is 1 over u. And then I find derivative of u with respect to x, and I'm just using notation so you'll see how I get the derivative, and that's 3x squared plus 2x. So all I do is simply multiply these together and write them in terms of x again. So it's 1 over u, which was x cubed plus 2x, times du, which is 3x squared plus 2x. Chain rule works on any function. You know, it could be something like this. Y equals, you have a, I don't know, x cubed plus 4x squared. And then that's all raised to the 10th power. So my mama function, the big function, is u to the 10th power, so a power of 10, and then the baby function, what's inside, is this x cubed plus 4x squared. So du is 3x squared plus 8x. Y, like I said, is u to the 10th when I substitute in, when I replace it, write it in terms of u. And so dy is 10 u to the 9th using my power rule. And then I simply multiply these two together, go back to terms of x. So 10, I don't want to leave u in my final answer. So u is x cubed plus 4x squared to the 9th times du 3x squared plus 8x. So that's an overview of the chain rule. They'll do more in depth on the PowerPoint and show all the notation and everything, but that's basically the process. Identify u, find the derivative of u, and then multiply mama function by baby function derivatives. All right. Chain rule, and then the next one is not necessarily a rule, it's just, I call it a mathematical trick to find, they'll say use implicit differentiation, and it's when your function is kind of a function, not a function of x, like y equals some function of x, it's more a function that looks like this. And, you know, I could solve that for y, but then I have a pretty complicated function to find the derivative of. So this one is easy to do with implicit, and implicit is all about using labels. I've been talking about like the derivative of y with respect to u, and that kind of thing. The derivative of y with respect to u, you saw that over here when I actually used my notation. So dy would equal 1 over u du if I kind of cross multiply here. This would be 3x squared plus 2x dx. So that's where implicit comes in. We just use our labels So so the idea to find the derivative is I'm trying to find dy dx, and that's the label I want to work toward. So the derivative of x squared is 2x, and then I'm going to put a dx there because it's with respect to x. Now this derivative is 2y, but that one is with respect to y. On the right-hand side, I have a 3, and that's with respect to x. Now all you simply do is put the dy's algebraically, use a little algebra, get the dy's on the left side and the dx's on the right side. So I'm going to subtract this one because it's a dx. I want to put it over here with the dx's. So I end up with 2y dy equals 3dx minus 2x dx. So what I'm going to do, for sake of time here, I'm going to pull out that dx because they both have a dx in common. So notice if I distribute that, I get this back. So I'm kind of skipping a step there to go quickly. So my final answer, remember I want dy over dx, so I'm just going to algebraically manipulate it here. When I divide by d, that's what I want. So I simply have to divide by 2y. So that is the answer I'm going to put into my math lab. The whole quantity, 3 minus 2x divided by 2y. So remember, this is finding the slope of the tangent line, so I know it's a function of x and y, but I can still find the slope. What would be the slope at a certain point, whatever, I don't know what they might give you. Let's say, I don't know, it'd have to be an xy coordinate that works up here. And then you'd plug it in and you'd find the slope of the tangent line. So that's how implicit works.